So today I will present my work, Can Machine Learning Benefit Bandwidth Estimation at Ultra-High-Speed Networks? And I'm not a machine learning expert. I'm also a beginner when I start this project. So first, I will give you some basic idea what's the common technique to perform bandwidth estimation, and then the challenges of bandwidth estimation at ultra-high-speed links, and I will focus on 10 gigabit links there, and then I will introduce the proposed machine learning approach to tackle the issue, and then finally evaluate the accuracy of the machine learning model. So available bandwidth is the capacity left by cross traffic from one end to another. Common bandwidth estimation tools will send a group of packets called probe stream or P stream for short from the sender to the receiver. And every packet in this probe stream is probing at some specific probing rate. And this rate is achieved by accurately control the inter-packet gaps. We refer to it as the send gaps. And this P stream traverses through the network, encounter cross traffic, and then received by the receiver side. The receiver will timestamp packet arrival and calculate the inter-packet receive gaps. Usually, bandwidth estimation is made by comparing the receive gaps and the send gaps based on the principle of self-induced congestion, saying that if the receive gap is larger than the send gap, it means that that packet must experience some queuing delay on the bottleneck link. Thus, that probing rate must be higher than the available bandwidth. So previous bandwidth estimation tools will find the maximum probing rate at which the receive gap is no larger than the send gap. And that maximum probing rate is used as a bandwidth estimation value. Previous tools tools can probe for a wide range of probing rate within each P stream. And here we have a 4-rate probe stream with a total length N16. And for this probe stream, starting from the third probing rate here, the receive gaps become consistently larger than the send gaps. And according to the principle of self-induced congestion, this is the signature of persistent queuing delay. Thus, the second probing rate will be used as the bandwidth estimation value. So previous multi-rate bandwidth estimation tools such as PathChirp perform fine on 100 megabit links, but if we scale up our link speed, we need to create very small inter-packet gaps. For example, in order to probe at 10 gig, we have to create gaps as small as 1.2 microseconds. And even if we use jumbo frames, that gap has to be as fine as 7.2 microseconds. Such fine-scale inter-packet gaps are so vulnerable to noise on the end-to-end path compared with lower link speed. And the first question is whether the sender is able to create such fine-scale accurate gaps. But in this study, we will ensure that the send gaps are accurate and within 1 microsecond accuracy, and we will focus on the noise the P stream encounter on the rest of the path. And let's look at them one by one. First, the cross traffic at ultra-high-speed networks can be very bursty. Thus, packet will experience transient queuing delays at the bottleneck link. So inter-packet gaps after the bottleneck won't be a smooth line, it can be such noisy. An even more severe noise is receiver timestamping. Let's recap. Ideally, the receive gap should be a flat line as this plot, but let's see the actual receive gaps we observe. This shows a very crazy spike and dips patterns, and previous researchers have identified that this pattern is caused by interrupt coalescence at the receiving NIC. The receiving NIC will not generate interrupt for every packet arrival, but it will queue up some packets and send packets in group to the operating system, and the timestamping will be done in a batch. So the spike corresponds to the first packet in that interrupt, which experience a huge queuing delay at the receiving NIC. Those dips correspond to the subsequent packets that queued up back to back within the same interrupt. So this spike and dip pattern totally removes the signature of persistent queuing delay, which leads to severe overestimation. So the state-of-art denoising techniques follow a smoothing-based approach. Some of them use a super long probe stream and a very large averaging window because it's instinctive that large averaging time scale will help us to reduce the impact of noise. For example, a tool called PRC-MT, we found that it requires 320 jumbo frames in order to probe at 10 gig robustly. One of our previous, so this long probe stream introduced huge network overhead. One of our previous denoising technique is called BAS. We focus on making shorter probe streams work. This BAS algorithm, it will detect the boundaries of interrupt automatically and average out within each interrupt. And with this algorithm, we are able to make accurate estimation possible for multi-rate probe streams with only 96 frames in it. And we can limit estimation error within 15% for over 80% P streams. However, in the context of some applications, this 96 P stream is still a large time scale. For example, in the context of congestion control, can we make this value even more smaller? And also, this human-designed BAS algorithm, it uses very simple heuristics and with fixed parameters to detect the boundaries of interrupts, which is actually an underfit model. If the signature of the noise becomes more sophisticated. Since machine learning is really a hot topic recent years, we're asking this time, can machine learning help us to understand the noise in inter-packet gaps so that we can enable even shorter probe streams than the BAS algorithm? Now let's see our machine learning approach. So our goal is to obtain a bandwidth estimator or a model that is learned offline. A typical machine learning process consists of two phases, the training phase and the testing phase. In the training phase, we will first collect a large amount of training data to some particular machine learning algorithm, and that algorithm will automatically give us a bandwidth estimator. Here the training data are P stream observations X and Y. Here X is the concatenation of send gap and receive gap observations from both ends. Since the noise introduced in cross traffic and in the receiver side interrupt coalescence will operate at different frequencies and will distort inter-packet gaps to different extent, now we apply a fast Fourier transformation to manifest its signature in frequency domain. And the Y values there in the training set is a vector of the ground truth available bandwidth for each corresponding X when that probe stream is in flight. Now we feed the training data to some machine learning algorithm, and that algorithm will discover the relationship between X, Y for us. And its goal is to minimize its predicted Y values and the actual Y values in the training data. In this study, we try a bunch of machine learning algorithms that are popular in the field right now, but we find these three doesn't fit our training data. But random forest, ADA boost, and gradient boost algorithms are able to give us a much more robust estimation than any human-designed algorithm. But in this talk, we will focus on the gradient boost algorithm here. Okay, so now we get a gradient boost model, and in the testing phase, again, we will have a lot of X-Y pairs as the training data and feed the X values into the learned estimator from the training phase and get the estimated available bandwidth. We will compare this ABS with the Y values in the testing set to evaluate the accuracy of our learned model. The metric we use here is the relative estimation error for multi-rate probe streams, which is calculated as the difference of between the ABS and the ground truth AB over the ground truth AB. Now let's see how we collect the training and testing data in our study. In our testbed, we have 2 10 gigabit switches, and we have a pair of machines with 10 gig NIC on either side. They will send probe streams and receive probe streams, so they will give us the X values for both the testing and the training set. Other machines on either side of the switch are responsible to generate cross-traffic. In order to make our experiment controllable and repeatable, we let each traffic generator to replay a highly realistic and bursty web traffic trace. And here we obtain aggregate cross-traffic, and this is the most type we have in our testbed, and we denote it as bursty CT or BCT. Also, we apply a token bucket filter on each traffic generator to obtain a smoothed version of BCT, and we call it SCT. We also have a completely constant bitrate traffic CBR, and replay other 3 packet traces UNC 1, 2, 3 that are collected on the egress link on our campus. And between the switch and switch, we attach a DAG monitor, which is able to capture packet trace at line speed. And we will analyze that packet trace so that we can obtain the ground truth available bandwidth, that's the Y values for each P stream. And now we have the X and Y values for both the testing and the training set, and we make sure that there are at least 10,000 examples in either set. Ideally, machine learning works best if every testing data is represented in the training data. This requires that the testing scenario have to be completely identical with the training scenario, but this is something you can never expect for traffic on the wild. P streams may experience different bursty levels of cross-traffic, and they may be received with different interrupt coalescence parameters, or IC patterns for short, at the receiving NIC. And even with the same IC pattern, if the receiving NICs are from different vendors, they may have totally different behaviors. And in this study, we will use 5 different burstiness of cross-traffic and a wide range of interrupt coalescence parameters and 2 different NICs to address whether the machine learning approach is robust to these factors. First of all, let's see the impact of cross-traffic. We first send out a large amount of probe streams encountering the most bursty traffic BCT and received with the default IC pattern at the receiving NIC. And we try out 3 different probe string lengths, 96, 48, and 32. And first, we apply the previously human-designed BAS algorithm. And here we plot the CDF of the relative estimation error. We find that when we use that human-designed algorithm, once we reduce the probe string length from 96 to 32, we get significant performance drop. Now, for each n value, we obtain a gradient boost model and apply them to the P streams in the same experiments. And here is the accuracy of the machine learning models. We find that for every n values, we can achieve considerable accuracy, and we limit estimation error within 10% for the majority of P streams. And here, with these settings, we find that the machine learning outperforms the BAS algorithm. But whether these results hold for all types of cross-traffic? By the way, later on, we will only focus on 48 P string lengths. And now, we send out P streams with other type of cross-traffic, and first we apply BAS algorithm. And here, the candlestick, we plot the 5 percentile to 95 percentile relative error, and the bars are 10 percentile to 90 percentile. And we find that the best algorithm, it performs okay, but now for each cross-traffic type, we obtain a gradient boost model and apply it to the p-streams within the same experiment. And here is, we find that the gradient boost model plotted as the red bars there, it reduces the inaccuracy of bars. So for every cross-traffic type, we found that machine learning outperforms the Bayes algorithm. Now let's move on to the case when the training cross-traffic differs from the testing cross-traffic. It's expected that a model learned with a more bursty cross-traffic can handle testing cases with smoother cross-traffic because that model is able to deal with more sophisticated patterns in the interpacket gaps. And now we apply the previously BCT learned model to other cross-traffic type, and we find that yes, our hypothesis is confirmed, and especially when we apply that bursty learned model to smoother cross-traffic, we can do even better than the model trained on that traffic itself. Okay. Now what if we apply a smooth traffic learned model to a bursty cross-traffic? Now here again, we apply the previously other traffic learned models to the BCT cross-traffic type. And we find that with the significant smoother cross-traffic learned model, we increase the inaccuracy. But in general, we are still doing much better than the human-designed Bayes algorithm. But this tells me that if I have the choice to choose the training cross-traffic type, still the bursty cross-traffic is preferred. And here we can also find that the machine learning algorithm compared with human-designed algorithm is robust to the noise introduced in cross-traffic. Now let's move on to see whether the p-streams are received with different IC params. Different interrupt coalescence parameters will decide the height of the spike and the distance between those spikes, and which give us totally different noise patterns. Now we have two NICs in our test bed. The NIC 1 is a NIC we used for previous slides. Its interrupting behavior is controlled by interrupt delays. Here we try a wide range of interrupt delays from 2 to 300 microseconds, but we used to use the default parameter, and its semantic is only clear to the vendor itself. Still, we first apply the Bayes algorithm, and we find that the Bayes algorithm it leads to severe overestimation for extremely large interrupt delay values. What if we apply the machine learning model with the default parameter? We found that the default parameter learned model, it gives much higher accuracy than the Bayes, but still it cannot address the large interrupt delays very well. Now we have another training set called 3 set, which includes the default value and the two extreme interrupt delay parameters 2 and 300, and this 3 set trained value plotted as the green line here is able to give us a robust estimation across a wide range of interrupt delay parameters. But whether this 3 set training is still robust for another NIC, now we try the 3 set on another NIC 2, and visually we find that these bars here are more taller than the one for NIC 1 because this NIC, its interrupting behavior is much less predictable than NIC 1, and we are not sure whether the settings of the parameters work. But here the 3 sets, it includes the data from the default parameter and the two extreme parameters for the number of frames it can collect before it generates an interrupt. And here, still we find that our previous conclusion holds. The 3 set model is robust to interrupt coalescence, to other interrupt coalescence parameters. Finally, let's see whether the model trained on one NIC is portable to another NIC. Here we have we do a cross-NIC validation in our between NIC 1 and NIC 2 with the 3-set training, and this here the black bar plots the case for the model trained on the NIC itself, and the red bar is the cross-NIC model. And we find that when the interrupt coalescence parameters are in the moderate range, the models are portable between two NICs. Last but not least, since the machine learning gives us so much benefits than human designed model, what's the overhead? Since our model is trained offline, so the training phase overhead is off the table. But still we have to load the model into memory when we do online estimation, and the memory cost we found in our Python implementation is totally affordable for modern systems. And the time you spend to estimate each bandwidth for each P stream compared with the time scale of each P stream that lasts for several milliseconds, this estimation time is just negligible. So conclusion, in this study, we propose machine learning framework to perform bandwidth estimation that tackle noise at ultra-high speed links, and this approach makes accurate estimation possible for even shorter probe streams and here we try the N48, and it's robust to various kinds of noise on the link. And also it only introduces a negligible overhead. And in the future, we are trying to explore NICs from more vendors and incorporate the learned model into a rate-based congestion control scheme. And that's all. Thank you for your attention.
Thanks for the talk. So these NICs, they have offload capabilities like interrupt coalescence. Some of them also can do timestamping.
Hardware timestamping, you mean? Yeah, but so here we are tackle the case if the NIC is not able to do hardware timestamping, because those kind of NIC are more expensive, and we are expecting that in future. The end system, especially in the small-scale networks, they will just use common 10 gig NICs without the timestamping option.
Okay.
Yeah, but I think even in that case, we still can benefit from machine learning in the case of dealing with the network cross-traffic noise. Yeah.
You put some fairly complex cross-traffic through, but the test bed involved basically just one hop. So have you tried it for multiple hops?
I think there's some previous study saying that even if that's only a one-hop topology, but if the packet trace is collected on some egress link, on the egress link between two large networks, is still in the test bed, this traffic is still representable, and the results holds for multi-hop networks.
I'm not so sure about that, but I'll let someone else ask you a question.
Yeah. I can refer you to a paper later.
But this is something you could test, right?
Yes, that's true. Yeah, but we need more resources in our lab. Yeah.
Any more questions? Otherwise, I guess we're a bit late, so we'll stop it there.